So let's get started on real reinforcement learning. You now have an understanding of the Markov decision process, hopefully, states, actions, and rewards, and time, right? The dynamics that are being progressing over time as you take your actions and the state changes. So now we pull these all together and we see that when we're talking about reinforcement learning, we're talking about maximizing our long-term future reward, right? That is really kind of a definition of the entire process. You might be having that you're maximizing your long-time future expected reward, or it could be discounted. So there's all these qualifiers that will get added to it. It's not a very good way to do it. That we'll see along the way. Right, so expected and discounted and could be approximately optimize, maximize. But generally is the idea. You want as much as you can over time as the world changes. So in bandits, right, we were trying to maximize the reward we get at every moment. But now we know that the world is changing and we can kind of build up those rewards. Right, so we had some returns listed before on a very simple kind of Markov decision process if you saw them. So now we combine a couple of those together and see how we're going to define them to become value functions. So the discounted return, just to kind of summarize that, would be the return you're getting at a particular time step, right? For taking some action that you took, and this would be the amount you got as feedback. So it could be the reward, or it could be the power level on your robot's battery, or the distance you are from the goal, like a negative of that. And what we're doing each time is having, if we have a discounting, right, so we have a non-episodic task, right, or we have a continuing task, we were saying that we'd often have a discount factor, right, which says that future rewards aren't as important as immediate rewards, right? You'd rather get the money now than later. But you still want to maximize the long-term reward over time, but taking these discounts into account, right? So if we look at a sequence of, say, the reward that we're going to be getting, given, that you were in the states that were given, and the action that you actually took, these are the rewards you're getting at every one of these times. I guess we could say these are, time t equals 1, 2, 3, 4 for all of them. These are rewards you happen to have gotten at those times. If we had this discounting of 0.5, then in the first step we're not going to have any discount. We actually get all of the reward, right? That's our return. So a distinction between when we say return, we're talking about the reward they're getting over time, discounted, maybe combined with probabilities and everything, right? So this long-term reward that we're maximizing is what we're calling the return, right? My pen is not working well today. We're calling that the return. So the reward is what you get at a particular moment, and the return is what you get over forever from now on. In this case, we have 2 steps ahead. We have 0.5 discounting factor, right? And so we're going to get 2 times 0.25, so we get 0.5. We're getting a quarter of that because it's 2 steps ahead, and we get 0.5 times 0.5, which gives us that reward, right? So you really can just compute it this way, right? So if we're getting 2 here, and here we know it's what? 0.5, right? But in this case we got 0, so it doesn't matter. In this case, we got 0. Right? So we're literally just computing this. Now this is the expanded kind of expensive form of doing it. So very quickly now we're going to want to remove that and get a more compact form. Right? So if you have a higher discount factor, then things in the future are going to be more important to you. Right? So the exact same situation where the reward 2 steps down the line was you got $2, 2 value points. Your return now is much higher. Right? So at this point, future rewards are more important to you. And in this case, you can overcome an initial negative reward because of future ones, but the discount factor still drops down quite a lot. So even though this adds up to 11 reward, it still kind of just barely gets you over the hump of getting a -1 right away. Right. So the next slides has a nice kind of example case with more kind of situations for you to work out. So I encourage you to kind of work through that. Maybe in a tutorial or an extra session, we can kind of go through this if people can't see where they're coming from. Just some examples. Okay, here's the discount factor, and here's the reward sequence you're actually getting. Then what would be the return you'd compute from that function. So try doing that out without looking at the answers. I should make a note to make sure we post the entire slide deck, because I don't know if we have yet, with the fill-ins on those questions. So if return functions and sums of discounted rewards, calling those returns makes sense, what we're realizing right away, those calculations, if you went through them from the previous slides from this, it's a bit kind of messy and you're going to lose track of this number and that number. What you really want is a functional form that explains what we're really getting at here, which is to gather as much, to find a policy for acting, to gather as much value, in a way, discounted rewards, information, probability, over time, so that we're improving our ability to behave almost in the long term optimally in this domain, right? So we can't say we're going to be acting optimally in this kind of domain usually under reinforcement learning. We're kind of aiming towards it, but what we get as an advantage for that, for perhaps not having optimal, is that we can learn from any situation as we're going. But we're actually going to start off with talking about the difference between optimal control and prediction of the states, and then kind of suboptimal kind of policy optimization or improvement. So we're going to define these two functions that we're going to use throughout the course. Upon the both value functions, we're going to have state value functions and action value functions, right? So they're going to be V and Q. So value, V for value, Q for Q. They're just two different forms of the same thing. These are kind of our mathematical language for describing decision making and values and the returns, really, expected returns. So we have that notation already for states and actions. We need this kind of one more element, which is how do we represent our target, our actual our goal in optimization, which is this value function. So building an estimator of what's going to happen next is one thing, but building the value of how good it is to be in this state, that's what V is going to be giving you. And Q, this action value function, is the same concept. It's just what's the value of being in this state and taking this action. So this is kind of the value of getting into a particular room in the maze or in the video game, and this is the value of opening a particular door or chest or something like that. Right? But they're getting at the same thing, and they're computable from each other. So the values that we're talking about here are expected return objects, right? So we've got our expectation operator here, where we're saying that the value of our policy that we're using right now in the current state is the expected return, right? So G is the return that we've been computing kind of manually in those previous things. The expected return that we would get, we would expect to get starting from time t, given that in time t, we're in some state s, and s is a particular state, right? So s is we got lowercase s here, right? So s is some particular state. As opposed to like all states, because here we're saying what's the value of s in this actual state. So this could be the state of being in, room 1, facing left, with power level on your robot at 80%, right? That would be your state. And it's literally everything that you know about the environment and the situation. It could be even the sensors is right. Ambient light level is 85%. It's bright. Things like that. This is in the state. So why was he saying that? So what's expected return? How much do you expect to get in the long run for being in this state and then following? So what's our notation here mean? We're not going to use this notation a lot. Usually it's going to be something more concrete like these things here in the second. But if you know MATLAB or Python, we're using colon kind of operator. So actions that you've taken from time t, so the action you're going to take right now up to infinity, it's a very loose notation, sampled from your policy, right? And so that squiggle is usually going to be sampled from. If you're in LaTeX, that's actually not tilde. Now tilde gives it to you on top of a symbol. I'd have to look that up. I think it's just sim or sample. We'll look that up. So what else? So in a set kind of functional definition, we're saying that this value function is a function from states to real numbers, right? And so we've got a couple different ones we're kind of defining here, and they're all kind of the same structure, but I'll just go through them. So if we look down to the next line, then we've got a state action value function, Q, where we have to look at the not just the state that we've taken, that we're in, but the action that we're going to take. We want to know the value of that we're going to store. So in a programmatic sense, V is an array, okay, a 1D array, or a vector, and Q is a matrix, right, or a 2D array, right, because we're going to have two indices here, the state and the action, and it's the same thing, would be the expected return that we're going to get by being in some state right now, so where your robot is in the room, and then the action it actually takes. So this is the expected discounted reward going to the future of being here at this spot and moving forward, and then following your policy for the rest of time, right? Sampling from this policy, whatever you have. So they're the same value, and there is a conversion, which we'll see, where the state action pair Q, the Q function, stores basically more information piece by piece, and the value function is that kind of marginalized out or summed out over A, right? Because you can imagine that if you combine together all the values for every action you could take in a state and add them together by the probability that you're going to take them according to your policy, then you'd get V, right? But we'll have that shown a little bit later. So it's easy to see here, even easier to see with the Q function, and we're going to go into more detail with these in the oncoming slides. But in the state value function QSA, we have the same things being recorded, the value of our returns of our actions being carried out into the future under a certain policy, whereas the policy pi here is our policy. We could talk about then the value function q pi, which is our value when we follow that policy. And so what if we follow the best possible policy, right? So if we knew in every state what is the best thing to do, because we knew the values of all the different choices, then pi star would be the optimal policy. This value function that is converged, and we know exactly what the true value of this is following forward under the same policy. If we always chose the best action in that moment, these would be the optimal value functions. And we're choosing max pi here because we're defining a function that maps us to actions at every state. I don't know if we have that defined. Later on we'll have it defined, where the policy itself could be defined as a function that goes from, I don't see it anywhere, right? The policy pi is a function that goes from states to actions, right? So it takes the state that you're in, this position in the room your robot is in, and it says, let's move forward, right? So that's the whole function that you're returning here, maximizing over. So we'll go through the next bunch of slides, kind of clarifying what each of these value functions kind of means. And right, the optimal policy is the one where we're always taking the best action, right? So there is some action to take at for every state. There's an action that's available. That's why it has a value greater than 0. And where we're always choosing the optimal action. So the value for the action we take is equal to choosing whatever action in the original function maximizes this value. So it's always choosing the best action. Right, and another way to talk about that is we're talking about greedy policies. For the bandits, you can take the greedy policy based on your exploration and try to exploit that. But if you know that your value function is optimal, so it really does represent the true value over time of taking that action, then you want to be greedy with it. That's one of the underlying concepts we'll be using. So if you look at these, you can kind of put them in a chart and consider these two different ways of representing the value, which is the state-based and the state action-based. And what you talk about in control theory classes is kind of this optimal control, right? Saying that there is a way to define that optimality. We set up the dynamics of the systems in such a way that we know we can find the optimal, and we try to just find this solution. So everything we're talking about in this course kind of relates to that, but it's kind of broader, because if you can't have the optimal, then what do? You're going to have to make a prediction. You're going to have a policy that works good enough, but that in the limit would be the optimal one. So all the processes we're having are an attempt to let you work in the prediction and decision-making space. In AI anyways, we'll often kind of talk about decision-making versus optimization. Oh, my computers. Between optimization and control as two different ways of doing this, but where we have a broader point where we might not be able to find the optimal.